I think I have my other device up properly. I think that should come up, and we should be okay with that. Okay. So intervals are important because they give you the ability to look at events that may happen, and you don't necessarily have to watch the event continuously. Only when the event actually happens that you're sort of prompted to, or the processor is prompted to look at the event, which is convenient because you don't necessarily have to spend a lot of time, should I say, seeking to see, watching a particular device or a particular input or a particular entry of anything. So that's why an interrupt, it's convenient in that manner in terms of it saves time in terms of the processor, and it also saves computation energy, or rather computation or basically. Okay, so if you had to find something, you have to pull something over and over again to actually see it happening, because everything that codes come sequentially down. So in order to see it again, you have to go back up and keep doing that same thing over and over again continuously, and that gives you a lot of wasted time. Whereas if you have an event that actually happens to happen, let me make my notes. I can find it. Well, if it happens to happen, then you're only going to see that event when it does happen. So that saves computational time, and the processor doesn't have to work as hard. So coding in that manner saves you a lot of computational space to do other things that are more important in that sense. But then you don't have to watch something over and over again. Whereas if you didn't do that, if you were more on simpler side of coding maybe, then you would have to pull and watch something over and over again. Of course, you can build in delays, and so that might also help in that sense. Okay. Okay, so I think I'm here already. So let me share this with you. And like the last time, I was indicating that I think I have too many things open. Let me just go some nonsense. I can't find the. I really can't find this page to share. Allow me to try again. Close some of that stuff off. Okay, now it shows up. Okay, so yeah, so like I said, you have these interrupts allow you to make reasonable reasonable use of your CPU time, your CPU space. Okay, so I think we've covered up to we covered all of this yet. I don't think we did. We think we were on. I think we were here until vectors. Okay, and one thing before I go further into this, there's one thing I have to revisit on subroutine. when you do a call on subroutine, and let's say you call something, you should put a pound sign in front of the subroutine name. So call subroutine 1, say. So that I believe you need a pound sign there. And before you leave a subroutine, say you have subroutine 1. I don't know if you did this last time. So you have this, and you do the iterations. You should also put a return. If that's not there, then you're not going to return back to the spot that you would have called it from. So you probably be going on further on. So you want to return so you can go back to the main program or whatever called it. So that's hopefully that if that was not the case, indicated in the examples that I gave, make sure that that's the case, that you have those corrections. Now, back to some interrupts. I think I had to make that before that goes over my head again. All right, so like I said, there are interrupt vectors that assign to peripherals, also to pins or your output pins, and to processes as well. So let's look at more or less the pins, because if you look at the pins, that'll pretty much all, I would say pins exactly, but in the sense of assigning the pins those functions, then yes. Then yeah, because you let's say you're working with the ADC or you're working with a timer, then those assigned registers would be associated, or any kind of interrupts would be associated with some way of sending it somewhere, or to a pin or something. Not necessarily. If you have an input or pin, say, you have to read that in, then those interrupts would correspond to those pins, and you're making those assignments based on those pins. I hope I'm not confusing anyone, or you're still with me on this, I hope, and you're locking into the words and getting it right in your head, and not talking in the air. So then, so say for example, the timer, this has a particular place, and this vector has a particular address, and then when we have this vector, it's assigned this name, but there's a vector that's associated, an actual address that is associated with this or a vector address that's associated with this particular interrupt. Right? If you have an interrupt on this, then you would have a particular vector address that you have to go to. And we looked at that last time. So let's take a look at that just briefly again. And forgive me, I gotta find it. I don't know where I left it last time. And hopefully it doesn't take this long. I remember it in the page number. And hopefully it wouldn't take that long. I don't know. Let's just look. I don't want to take forever on this again. Okay, so let's what is that again? I need your class user's guide. Okay, I got it. Oh, I don't want the user's guide. I want the other one. Device data sheet. So in your device data sheet, it's because it's so specific. I think I'm there. Thank God. There's a memory function that, I don't know, this new Bing, or is it Bing, or maybe Microsoft, whatever this is. So once they start showing something, and it was and I click back and then I'll try to get back to the same document, it kind of goes back to where it left off. So that's a good memory point. Okay, so let me. Am I still sharing on that one? Yeah, okay, I think it was there. So yeah. All right. So this is basically the device data sheet, and remember the interrupt types we have. So we have a system interrupts. That's this one. It has to do with how the device functions in terms of like, for example, device on the power. Look at power and any other management related to the function of it. So if you have a brownout or a power reset, those are all have to do with the system reset. Power, brownout, the supply, supervisor. If you don't have the right amount of voltage going to the chip, those are all interrupt. This is a system interrupt, and reset the system. Also, if you have watchdog, that's another one too in this regard. Or some password violation if you have a password set up for your device. This is also a FRAM. So anyway, so those are all system resets. Then you have the non-maskable, and those have to do also with some sort of operation of the device. And that includes some, like if you have a memory violation, or you have some, what's it called? Timer, like your clock violation. There's some of that. And there's another one, some other, there's also something to do with your memory. So anything like that, this is non-maskable interrupt. But those are managed by your system, so you don't have to really worry about those. Those are all managed by a system. From the non-maskable to the system, those two types are managed by your device itself. You can use aspects of those to code and to watch your system, but you don't necessarily, especially at this young stage of working with this device, you don't necessarily need to interact with that as much or at all even. But what you do want to work with is the maskable ones. So from here on down from this point where you see comparator E down further, where the oscillator falls here and the external NMI, these are all non-maskable interrupts. And your user's guide describes them too. Okay, so the maskable has to do with that GIE bit, and that's in the status register. So all of these things have to be paired with that. So which means that you will have to activate that in order for any of these maskable. That's why it's called maskable, because that bit masks the interrupts that you have. So every last one of these has to have that GIE bit in status register, going all the way down to the last one here. Notice how long this is, but it's from priority to highest priority. Look at this, going down to the lowest priority here. Okay, I want you to notice what's at the higher level of this priority, beginning from the comparator. So this has in terms of the maskable types, this comparator is at the very top. Then you have the timers, and then you have USCI. This has to do with, or the watchdog timer. Sorry. Then the USCI that have to do with the transmission, right? That's universal serial communication interface. So that's, and then the ADC comes about. Then another timer A. So timer B is more important than timer A, it looks like, priority-wise, and interrupts. And then you're looking at more of this going down all the way down to the ports. Those ports 1 and 2, and all the way down to port 8. Port 8 is actually one of the lowest priorities, including this LEA. I'm not so familiar with this one. I'm not sure what this is, LEA, but it's somewhere in your data sheet, so you can look it up. So that's the lowest priority. Okay, so that's basically where you want to come to. And all of these have addresses. So these right here on this list, this list of this column, these are your addresses. So you can actually write to these addresses, and instead of writing to those, you can You can assign these address. You can actually have these addresses directly written too, right? The same thing as, let me go back to my lesson here. These names, these assigned values here. Wait. Sorry, on this side. These are vectors, and these have those numbers assigned to them. So on this side, this would be port 1 vector. Is named that, but this is defined as, if you go back to this document on here. Where am I? Here, sorry. So I find port 1 vector. This will be, where's port 1? Port 1 here. I have port 1. This will be OFFDEH. OFFDEH, right? Or OFFDE. You know, it's hex. So that's that vector and that address, basically. Okay, so that's what this is, the sign, and this is how it's defined. And the same for all of these other ones here too. Okay, that's all I can say. The reset vector is it's in your system. That's also shown here on this. That's all the way on the top here. That's up here, the reset vector, and that has to do with this. Okay, all right. Let's look at so system reset. That's basically what that is. Hope everybody still on the same page. Let's go back to this. So let me give the procedure. There's a certain procedure that's followed. Let me find another bit of notes that's on this topic. I put that now. And it lists this procedure on this pretty well, I think. And I believe I pulled it from one of the data sheets on one of the users' guides. I don't think from this device, but from maybe my device or another device in one of the earlier course offerings of this class. It's been a while since that was the case. So let me just find it and share it, because I think the listing is quite decent. Where is it now? Okay, I found it. Let me share it now. Let me stop this one and go to that. Okay, so really, this is basically just a little topic on the drop, and I started with those things, just talking about those things we just spoke about a little while ago. There's a picture here of what's the priority going to the lowest, and you can see this is in your, this should be in your user's guide, because it came out of one of the user's guide for one of the lower devices, and it shows each of these internal structure, basically these blocks, and system to kind of usages, right? Going from each of these devices that you have going here from high to low. Anyway, so that's a depiction in terms of your device directly in terms of the physical hardware. Okay, we've been talking from a software perspective. Now this shows it from a physical perspective. So that's in your user's guide. You can look at that too. Okay, and also this is also another version of the same thing we looked at earlier, but from user's guide. You cannot specifically put it because it doesn't have it, and depending on your device. And so here it is that same, for that particular device, this description of what we had. Now I'm going to get to this one. So pay attention to this. So any kind instruction is completed. This is when you have an interrupt. So let's say you have an interrupt and the software sees it. First thing it says, any current executing instruction is completed. So the PC then points to the next instruction, is pushed to the stack. So notice that that goes to the stack. And the SR is also pushed to the stack. Status register is pushed to the stack also. Then the interrupt with the highest priority is selected if multiple interrupts occurred during the last instruction and are pending for service. Then number 5, the interrupt request flag resets automatically on single source flags. Multiple source flags remain set for the servicing by software. So notice that the flags the flags have processing too, right? Then the status register is cleared. This terminates any low power mode. Because the GIE bit is cleared, further interrupts are disabled. Okay. 7, the content of the interrupt vector is loaded into the program counter. The program continues with the interrupt service routine at that address. So notice that it actually goes to that vector, and these are some of the things that happens when an interrupt occurs. I think this is the end of this document. Okay, yeah. So those are the procedures, and this is kind of give you a scenario of what happens. Okay, so I want to show you that because notice the couple of things that you want to make sure you follow: the program counter, the SR, and also those flags. And you want to track those flags and make sure you clear the flags that are associated with your interrupts, especially when you leave them after you've serviced the interrupt. You should clear your flags also. So make sure you do that. Let me stop the share on this for a minute. Let's go back to my notes one more time. And so I think I was here. So let's look at the interrupt service routine. So you pull up my stuff in this book. So interrupt service routine is where you service the interrupt. So you made a call, you have your interrupt set up in your main program. Now you have to worry about how you're going to execute this interrupt service routine. Okay. So this is the interrupt handler, right? And it's a code block executed when interrupt occurs. So this is where it does the function basically. It looks at the function and it executes the function for you. So it's like they say here, it's very similar to a function or a subroutine. However, unlike a function or subroutine, the ISR is called or requested by the interrupt, right? The microprocessor or microcontroller does not allow for nested interrupts. So make sure there are some controllers that do allow for nested interrupts, but in this case, the Texas Instruments device that you have does not allow for nested interrupts. And nested interrupt is you can have an interrupt. You have an interrupt, and then that interrupt calls another interrupt, and that interrupt can call another interrupt. So that's like 1, 2, 3, basically nested. Not necessarily just that, but that's a scenario, right? So one interrupt. Say you have an interrupt, and you go to your service routine. That service routine could call another interrupt, and that interrupt necessarily can call another interrupt. This doesn't happen. So take that out, and just the top level interrupt is what's happening with this device. So therefore, it's important in this case that it is the interrupt service routine is very short. It must perform its action as soon as possible and return service back to the main code to allow other interrupts to occur. I hope that's clear. So the idea is to make the interrupt service routine as short as possible so that you can allow for other interrupts to do their thing. You don't want to make it exhaustively long. And so they also make sure that to include the idea that you want the related interrupt flag to be reset at the end of the interrupt service request. That's important, so you can release that interrupt request to other interrupts that may occur. Okay. All right, I hope that settles that idea. So now I think there's a iteration of interrupt service routines shown for C, and then also for in assembly language. So let's take a look at what happens in C. And the reason why we look at C is because you may have a code, or you may have some kind of processes that might be in the C program or C programming that you might have to translate from C to assembly. And so that's why we look at it just briefly. Not much to go on, but briefly. Okay. Now, everybody understand what an interrupt service routine is, right? Everybody understand what an interrupt service routine is? That's like the call function. You have a service routine, and it services the interrupt call. That's what the function of it is. So let's assume that you have an interrupt, and you say you enable your interrupt. So let's say you enable your interrupt, and so basically you have a set that happens to enable your interrupt. Say, then down further, you're coding down further down. Then you have your interrupt, right? So this in this case, interrupt P1 ISR. Okay, and so in this case, you write your code, and then before that you have a RETI. So this part is what you want to create the function for. And so this is what we're talking about now. But I don't know if I'm showing this. You can see this on your device properly. I hope you can see this. Let me pin my. So basically, I'm saying, so let's say in a code in the main program or somewhere in your code, you have your interrupt enabled. You have your other code that's there, doing whatever it's wanted to happen. So whenever this comes up in your main program and say that occurs, if it occurs, it should jump to this. Say for example, if this is associated together, those two are, and this is general. This is a little bit more specific, but let's assume that this is on pin 1, and you have your ISR. So whatever is in here, so I would have code, and then I return from it. So if this ISR, basically, let's assume this is to turn on the LED and leave it on, or turn it on and then turn it off with some delay, say, then this, then you can call this function as many times you need to do that, all right? But this services at a drop. Turn your LED on and leave it on. Let's assume that's the case. And when you turn it, return from it, you can actually have that. Return from it and do whatever you want to do. Or you can turn it off for a length of time and turn it off again. And then return I, which means come away from this interrupt service routine, right? So if this have a delay for some particular times, let's say turn it on for 10 minutes to allow for some, it could be like a water pump. Turn it on for 10 minutes and water your plants, and then say, for example, and then turn it off again after 10 minutes. So that's your routine, and it does it. And then after you finish, it returns back to the main program after it does its job. That's basically what we're saying. Okay, so it's going to assign a function, and this is the search routine that we're talking about now. So, okay, let's go back to my notes then. Hopefully that makes sense. I don't know hopefully it makes sense to you then. So in this case, although the classes we get to assembly coding, right, it's useful to discuss this in terms of the in C program. So the pragma keyword would be used in defining the ISR in C. Whenever you see a pragma, there's a bit of coding here. So, for example, it says pound pragma vector equals port 1 vector. So you see that it defines the interrupt vector. And then when you come here, you would see how it calls it. So this is underscore twice. Usually happens twice, and then drop void port 1 ISR. So this is actually calling this interrupt service routine. Okay, and in order to once it calls it, then you would go to the interrupt service routine a little further down, and this is where it occurs. So when you have that, you would see that this interrupt service routine has whatever it's supposed to do, and after it's done doing its whatever it's supposed to do, you want to reset your flag or clear the interrupt flag for this particular interrupt service vector. So clear that flag and then return I. And it's not showing that, but it's supposed to have return I at the end of this. Okay, I think that kind of sets the idea or tone for what we're thinking about. And C language, do they have a return I don't, because you have the pragma, I think it handles it internally. Does it? I don't see it. Actually, the brackets, I think the squiggle brackets is what's terminating this. So you don't necessarily need it. But. So yeah, so this is your routine. Okay. So so this pragma, so this is basically your interrupt vector, right? This is doing this. This basically gives you your interrupt service routine, right? So from this point on to the right here. So once you have that, you can see how it works out. In the main code, you would have something like enable interrupt, and it will look to see whenever that interrupt occurs. In the main program, you'll have that. That's not showing that here, right? So that's I think that makes you would see something like underscore, like I showed earlier, underscore enable interrupts, like the program that you guys run on lab 1. You'd see that underscore, right? And make sure you have it twice. Sometimes this line gets joined together. It looks like a long line, but it's actually 2 underscores. And I guess depending on the font, these will kind of sort of connect together, and make sure you know that's not just one of them. You have to make sure that that's the case. But in this case, you actually defining this, right? But then also in this other case up here on top of this, before this call, you have an enable interrupt. So make sure you understand that. Let me stop this twice for a minute. So make sure you understand that there's an enable interrupt further up, and then you would call your ISR. Okay, so that's important to remember for C language and for, I believe it's for both. In this okay, you would need this for your C language actually. Oh, it makes it work. You need this for the C language, and all you need in the assembly is basically you enable the interrupt, and that's using the mask, the GIE bit. Once you enable that, then you actually have enabled your interrupt. It's the same thing basically. Okay, let's so hope that makes, I don't know if that makes sense, but hopefully that makes sense to you. Okay. In C language, you need the double underscore. In assembly, you need the enable interrupt for the GIE. And that's just simply setting your GIE bit. Make sure you said that properly. Then you're good. So you bit set your bit set or bis.w GIE, sorry, comma SR. You move that into your SR register. Make sure you upgrade that. I'll set that bit. And then that's the equivalent of doing this. Okay. All right. I hope that's not messing anybody up. let me go back to the code on this so you can see what the difference is. I don't want to mess you up, and then you say you don't know what was happening there. Okay, so okay, so the underscore interrupt keyword should be added before its name, right? And you notice that there are two underscores given, and so your main block to be added here. You have to have the underscore interrupt, and that would start your so your enable interrupts comes with that. So enable all interrupts. That would be that text, and then you have the interrupt service routine that happens right here. Okay, so when it's that pound pragma, this is where your interrupt service routine starts. It goes to this vector defined in your data sheet, and then it would execute. It would give this underscore interrupt void port again, ISR void. Okay, and also and within that you have the brackets here, and it writes the code to that. Okay, so that's what it does. So you would write whatever your service routine is, and your ISR, your service routine code to be added, you put it there. Okay, and then you want to clear the interrupt flag afterwards. So this ends the code in C, and notice how the interrupt service routine is defined at part one, and at the very end, interrupt flag is reset before exiting routine. Okay, so that's that. Let's go to the next one so we can be more clear on this. So in assembly language, there's a little difference here. There's no pragma. There's no pound pragma. In fact, the pragma keyword is not needed. And so to start the interrupt vector, we can define it here. It is needed to link or associate the ISR with the interrupt, right? So you need to know how your ISR is going to be linked to the interrupt. Otherwise, you're going to miss your target. And replace the interrupt vectors and the ISR association at the bottom of the code block. So that's basically saying you need to know that you need to enable these. You need to look at this port and need to be able this port address, and you also need to make sure you know that that's pointing to that particular ISR as you define it up here. If you do define it, okay. All right, let's take a look at what it does first. Okay. Okay, so remember the ISR is a subroutine. Okay, that's not so important. And the only difference is the RETI instead. Okay, instead of the RET. So RET isn't for subroutine. RETI is for the interrupt service routine. Okay, so the reset label associated with the vector is associated with the reset vector. Right. Notice the system reset label associated with the reset vector. So that's kind of setting this up as if you were doing. You have to have your vectors associated with your programming. So this is the first one. This is from your system, and then up to here. Then this is the one that you would have set up, and this is your first one is your port vector, and then you have the routine itself, that label. You need to have that as .short, so that this can know how to link the two, and then you have to end it. Okay, so that's what we're pointing to, and so with your code, first thing you have your assign library, and you have your reset this and all the other things that you know would come along. The main code would be added here. So you would start it here. we don't have a main code anywhere in this for now. But you're at some point you're gonna have your I don't know if this doesn't give you a lot of detail inside this code, right? But remember, you have to have your mask, your interrupts enabled for your devices, whatever you're using for it, and you also have to have the mask enabled also to make sure that you have the maskable interrupt occurs. Then you have your ISR definition, which is this. So this is actually where your service routine occurs. So you write the code for your service routine, and then you want to make sure that you clear your flag for that routine and whatever location it occurs, and then you want to return from it. Okay. Then you want to declare some things. So you have at the end of your code. This is typical. You see that in your at the end of your program in your coding, you have the .global stack end and also the .set stack. So remember that's associated with your stack, how that's defined. Okay, now you have the interrupt vectors and how that's defined. You have the system again. I'm doing this over again because I want people to realize that those are important. And if you don't have this, then you're not gonna have this set up properly on this. Notice this is a label. This is a label. Even though it's not lining up on the left side of this, it comes in front of it though. So this is your ISR definition. So you can actually put this on front and not necessarily place it on the label area because it's an interrupt. So you can do that. You can get away with that. And then you have .short for reset and .sect for first vector, and then .short for the name of the interrupt. Okay, and then you have .add. Okay, I hope that makes sense on this. Okay, I hope that makes sense. So in the main program, all interrupts will be enabled, and as the interrupts occur, routines will be activated and executed as they occur. If there's no interrupt, your service routines will never have to be activated or never be used. Okay, so that's it. That's pretty much the way to set up your interrupt. Any questions on this? Everybody following on what I just we just went through? Because that was a good 30 or so minutes of me speaking. So I would like to know if everybody were able to follow. Was it okay?
Yeah, it's okay.
Okay, good. Now it's up to you now to more or less execute some of this stuff. Let's see if I can look at some more of this. Let's see. So so this example, we had looked at the port interrupts, and in terms of the port interrupt, so this is IO ports 1 and 2, and this older nodes that's assigned to that particular device of the MSP 430 F5. What's that device called again? 5529 MSP 430 F5529 Launchpad. So that's the one I have presently, and also for the MSP 430 F2013. Those two specifically I know because those were the devices we used in the past, and so I'm going off of those because in this case the 2013 only have 2 ports, I believe. I don't think it has more than 2 ports. If I'm not mistaken, I don't believe it has more than 2. And if it does, These two ports are the only two ports that have interrupt sources. I believe these are the only two that have interrupt sources for the MSP430. I think that's the case, if I'm not mistaken. This is a device that has a thumb, look like a thumb drive, the 2013. It's assigned to, it's not only just that, because you can put it on any board you want, because it's actually just a chip, one small chip. But what they've done is put it on a board that has like a thumb drive. You can stick it into your computer. And on the end of this thumb drive, there's a little small detached area. You can detach it once you program it. You can detach it and run any kind of like any kind of circuit, any kind of circuit process. So you can, let's say, run your motor controllers off of this once you program it, or run some other, any task, other tasks you might want to run off of it. So that's what makes these devices powerful. And so once you program it, you can assign it to do this little circuit board, and you can assign it to do whatever you want. The pins are assigned. I think there's a row of like maybe 10 or 12 pins. I'm not sure if I remember exactly. Maybe it's 14 pins. Okay, but that's that. That's that device. Your device, you have ports 1, 2, all the way up to 8 that have interrupt capability. So ports 1 and 2 on that device, and I believe it's on this one too that I have. Only ports 1 and 2 have interrupt service requests that can happen on it, or interrupt ability. But your device have all of the ports. So just read the data sheet and you'll see them. It's right there anyway. So I just showed them to you. Okay. Anyway, so the interrupt flags can be used to overcome, well, what's this says? Each pin of these ports can be used for a different interrupt, right? So each one of the pins can be used for interrupt. This is limiting, and so what is limiting is that each pin of each port share the same interrupt vector. So that's a one difference. Just remember that this shares the same interrupt vector, so that vector can be assigned as such. So you just have to remember that. And interrupt flags, can be used to overcome this issue. So that's why you have to reset your flags so that your pins will do what you want them to do. So it means you can independently control it if you know what your flags are. Your flags are there for each one of those pins, so you can actually do what you want it to do. Okay. So as such, related interrupt flags can be used to control what happens to these pins. So these are there are special service registers that can control control port interrupts, and interrupt enabled register PXIE. So whatever port or whatever pinout you're using, the X applies to that. Okay, so these edge select registers and the flag registers now, so you can actually use those effectively, right? This edge means that either you're on the positive edge or you're on the negative edge, right? So if you're on the positive edge, you can see when you can see how that transition happens. Let's assume this is on your input pin, input switch 1, say, as on your board, right? You press the switch. So as it sees the voltage going up, the transition will give you that interrupt. And also your interrupt flag will be set for that pin as well, for that particular event, right? And also if you have it set for so if it's up, then you look for that. If it's down, you look for when it transitions down. Okay. Okay. So that's what that does. Okay. There's an interrupt enable for each pin. So interrupt. Just remember that PXIE. Okay. And then you have the interrupt enable select. So this will select the edge. Okay. Again, and then you have the flag. So this will give you the interrupt condition for that particular pin. if you assign it, and the flag for that particular pin. Okay. Remember again, the vector is the same for all of those pins on from P1.0 to P1.7. Same vector, but you can use the flags and and those edge select also. You can use those to maneuver in your coding. Okay, so let's look at some. This is an example for interrupt. So in assembly language, let's look at the first example. Here we have the red and green LEDs. The button is pressed instead of toggling the red. Wait, what color LED? Have you guys ever used your second LED? You should have, because I think there's some homework assigned to it. Do you have a red LED? My device have a red LED and a green LED. What do you guys have?
I think red and green.
Red and green. Okay, so that's good. So one of the LED is red and one is green. So then you can see how your device switches across the two, and you don't have to confuse which one is LED 1 and LED 2. Okay, so in this case, looking at this program, so we're gonna set this up such that from the start you have on pin 1.0 or P1.0, this is set up as your output. And everywhere else looks like, in this case, on this particular direction, set up as inputs, right? And if that changes, then you'll have to see another one of these P direct out, so that it will P1 DIR. You'll see that change later on if you want to change anything later. But for now, this is all of the other pins are inputs, and this one pin on P1.0 is actually an output. Okay, so now the next thing it does is go to 4.7, and it's just 8 gives you 4.7, and this is P4 DIR. This 8 is 1000, right? So 1000 gives you pin 7. That's the last pin on. If you're moving from right to left, it's the last pin position because it has a 10000, and then the next half is 00000. That would give you that pin. Okay, and because it's on port 4 there, then you know it is correct, 4.7. Okay, the next thing we want to look at is this move 01 to P1 out. So right now you're writing a 1 so you're writing a digital high to P1 out. So you're setting this high. Okay, you're turning it on then you're going to move also on pin 4, you actually turn that on as well, because you're actually moving this value into P1 out. So you're writing to the output pin, you're changing that, and you're writing it and setting the pin to 1. Okay, the next thing you do in this case is you move 2 to P1 enable. So 2 is actually 10, right? No. Yeah, 10. 2 is 10. So that's 2.1 then. 2.1. I don't know why I just have 1.1. This should be 2.1 here. And this should be, I believe this is P2. So you're supposed to have P2 there too. I don't know why this is so wrong. So this is setting up the P2. So this should be P2. Let me write that in. It should be 2 there, 2 there. Okay, so those should be activated. So I think this is P 2.1. So you're writing on P 2.1. So this is your switch on pin 2.1. Let me make sure this is. I think that's the case. Here's my light. Yeah, this is 2.1. Should have been 2.1. Don't know why it's it's one. I think that's a mistake. I think it was copied over from somewhere and maybe didn't update anything. It looked like it levels through all of this thing. This actually should have been P2 here, P2 out, because it's actually activating this actual port with a pull-up resistor. So this is why this is needed right here. Okay, and then to really activate it, you have to write a P2. This is a P2 out. Okay, P2 out on this one, and that's how it's activated. So, okay, the next thing you want to do then, in this case, is you're enabling your interrupt. This is also P2, and this one too. Boy, this is a lot of mistakes, and also this one as well. Okay, so this will be 2.1. Messed that one, so I can undo it. No, I can't. Erase it then. I kind of like this draw function on this thing. You can make corrections on your notes. 2.1, this is all of this would be that. Okay, if I can scratch it. Okay, so that's what it should be. All right, and so you have enable on there, and you have this is on the. This looks like from the high to low edge. So this is high to low edge in this case. Then you go on from the IFG. So you have a flag that you're gonna clear a flag there too. Okay, and notice that this is where your interruption is enabled right here. So this function. That's like the underscore. Let me just write it up here. Underscore enable interrupt.
I got a question.
Yeah.
That 80H by P4.7, that's correct?
Which one?
The 88.
Yes. 8. Remember 8 is 1, 0, 0, and 0. I'm not writing these zeros good. So that's number 7 on the list. So then you have a bunch of zeros here. 1, 2, 3, and then 4. So that's P 1.0. No, wait, we're on 4, right? Okay, so P 4.0, 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, and 4.7. Right? Let me do that one more time. So P 4.0, 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, and 4.7. So that 8 is correct, yes. If you want to make sure that if you're still not sure, remember that this is 1, 1, 1, 1 is 7. And the next one up would be you have to be 8. So it have to be 1, 0, 0. Right? It have to be 8. Okay, anyway, that's what we're looking at. And I was stating that where was this coming down here? So where this GIE here is where you have this enable. And I believe it's spelled enable in terms of the C program. Enable underscore interrupts. This is a comparison, but you don't need to write this in anywhere. This is just a comparison interrupt. And I think there's a bracket around the end of this too, if I'm not mistaken. Yeah, bracket. And another bracket there. If you remember your C programming. Okay, that's what this does, and this is also that's what this is the equivalent, sort of like the equivalent of that. So that it writes your GIE, your status register. So this is your enable interrupt. And so once you have this mask, this is your mask, and then it would, and then you all have to do is when you jump to your dollar, all you have to do is wait for your program just to watch watch to see when you press switch one. Switch one, remember, is on 2.1 port. So switch one, once you press that, then you would jump to this service routine. And this service routine says toggle P1.0. So you're going to toggle P1.0. You're also going to toggle, you toggle two things. You're toggling P1.0 and also this is number 4 would be what? 1.0. So this is 4.1. How's it work again? There's something else you're toggling. I can't remember exactly what this is. 4 would be, let's see, what's that? What's that? 4 is 3, 4, 1, 0, 0, 0, 0, 1. Okay, yeah, 1. So it'd be this. This is a bit pattern. 4.6. This is 1.6. 1.6 and 1.0. I'm not sure why they have the 4.1 there. I'm not certain. This one, anyway, I don't know. I can't remember. But in any case, I'm pretty sure it's going to toggle this P10. And if it's 6, I don't know what consequences that would be on this. I think we set up 6 anyway. But I don't know if that's a typo or not. But we know that it's going to toggle the P10. That's what you want. And you're also going to toggle the 4.7. You have it written there. 4.7 is the other LED. Okay, and then you have the bit clear. So you clear the flag also, and then of course this is return I once you're done. And notice that you have these port vector 1 and your dot short on your P1 ISR. And then you end. That's the end of your interrupt. Okay, so this is how you set it up. Okay, so all right, I hope that makes sense. Any questions on that? We see how this works, right? In this case, notice this is where your interrupt service routine, and it is a nice ISR at the end of this. Kind of helps a lot in terms of showing what you're calling. And you notice that this has a dot short. If you leave this out, you will not be able to define this as an interrupt, right? These two are associated. Also, the port 1 vector, you need that also. You need that also defining when you're calling this function. You need that port 1, and it's associated with the when you set up this enable, port 1 enable. You needed that. Okay. I think that's a good bit of info on at least one of your interrupts. There are interrupts for a lot of different things in MC430, including your ADC, your timers. We showed them on the chart. So all of those vectors, are associated to those peripheral devices are there as well. Okay, let's see. So what are they showing next? Wait, let me entertain questions. before we move to the next example? Anybody have any issues with anything? So that was a good example, I thought. Okay, maybe let's move on then, since no question. Everybody seems hopefully you're following this pretty easily enough. Hopefully. Wait, let's pause there for a minute. Let's discuss your final exam for a second, because if I go and not mention it, it's right. Final exam. The final exam is a good bit of time, so I was gonna need about 3 hours to do it. So I need a particular day that will serve as your final exam. I requested some days, but Miss Brown has not returned any and I don't see a new schedule out. She hasn't returned my request.
So exam day yet?
Not officially, but I'm gonna set one up, because but I want to set it up during the exam phase of the time, because it will probably be easier, because you guys are pretty much in the same program. You don't have people from all over the place like some of my other classes.
So you say the exam for 3 hours. A lot of that time for a small coding project. Eh?
Yeah, the whole exam is on coding, basically.
Yeah, so we just can need the code compressor, maybe the compose, and that's it.
No, you have a short answer section, and then you also have some multiple choice questions, and also you have some parts where you code. So they're like the last section is where you code. There's parts 1 and 2. So one is where you answer questions, and also you have small coding examples given. Still coding. So no matter how you slice it, it's going to be about coding all the way.
About how much questions we're gonna get?
I don't know. Maybe I don't know.
Make sure consider thinking time now. If you could do the test in half an hour, then maybe need 2 hours.
5 hours.
No, this should be reasonable. I don't think I'm gonna do it to the point where you cannot do it. So that's why I asked you guys to practice your coding, and that's the reason why I've been giving a lot of coding for homework, and hopefully y'all are doing them. I don't see everybody doing them, and I think that's a mistake. I'm pretty sure that's a mistake. Please do the coding.
We try and Mr. Turner, but we get in it.
Okay, all right.
So you don't mind if we turn them a little bit late?
I do mind, but I at this point, not like you do at this point. Please turn them in. I mean, if I were you, I would try to turn them in a long time. But
you won't take off marks, and then
I can't tell you I'm not going to take up marks, especially the ones that are before midterm. I probably will, but the ones after midterm, I'll try not to take up as much marks.
Yeah, I was talking about that. The one after midterms, not before.
Yeah, but you guys should have turned them in already. But try to turn them in. And it's better to turn them in than not turn them in. So I don't especially if we did them.
Whenever we turn them in and you grade them, make sure comment, please. Like, I know ain't no way able to get 100%. So wherever I lose mark, let me know, and let me know they do wrong if that's possible.
Yeah, I'll try to do that. The issue now is time. I don't have a lot of time before the end of.
But Mr. Turner, I see this.
I will try to do that. At this point, it's kind of tough to do that, but I'll try.
I see this exam set for the 2nd of next month.
Oh, you do have a schedule. Where do you find a schedule? Was this sent to you?
I think so. I think we got that in an email. I ain't sure.
Oh, okay. Let me see.
Yeah, we got an email.
Oh, okay.
Actually, if you don't get no exam date yet.
I'm gonna look at my email right now. I don't remember seeing anything like that. Let me look. That's good. I didn't expect that. Hold on, let's see. This is sent, I guess, second, huh?
Y'all can hear me or y'all can't hear me?
Now we can hear you.
Oh,
Okay,
they sent it out again. Okay, let's see. Now I see it.
Yeah, it's for 12 o'clock.
12 o'clock. Really?
Like an hour and a half exam, man.
No, it's not half an hour and a half. Wait, I don't see this. I don't see this listing. Well, there's some information instead. I don't see it. I'm not seeing something here. Let's put on there. Yeah, I don't see it. I don't see the exam at all. Some information. Let me look at it one more time.
You don't see the exam or you don't see the schedule?
I don't see the schedule. So let me write that schedule down. What did you say it was?
It says December 2nd.
December 2nd.
At 12 p.m.
12 p.m. Okay. Tell me something. Do you see anything from MUSI 201?
Give me a second. MUSI 201?
Yeah.
Okay.
Hey, Mr. Turner, what is the weight of this final exam?
That should be on Moodle, but let me look at it. I don't remember what it is exactly in my head. Let me look at it. I think it's either 30% or 40%. I'm not sure which. Let me look. But there's a good bit of weight though. I mean, either way, you look at it. Let's see. Grading schedule. Right on top of your Moodle, you see something called grading schedule. And that is showing up as the final exam is 40%.
You say 201, you mean 302 it?
No, 201.
All right.
You see 302? What's 302 time then? You saw 302?
Yeah, she is 302.
What is that time?
That's December 2nd at 10 a.m.
December 2nd, 10 a.m. They must have made a mistake on that number. I have 302 as well, so that's, I don't know why they put 302. Maybe they look at my schedule. Yeah. So that's the wrong number, but that's fine. I'll substitute that in for that time. Wow. So you don't see a 201, huh? No?
You're still looking. Give me some time.
Sorry. Yeah, so that would be the okay. I don't think if it's not in the first week or the second week, then I don't think it's gonna.
Yeah, I don't think it's here.
Yeah, it's not gonna be there. Maybe they made a mistake on the 302. I hope I didn't send them it for 302, but I think I would have put the 201 in the message. So I think they made a mistake, but that's okay. I'll work it out with my 201 class.
Mr. Turner.
Yes. Yes.
The coding part you want us to do on a computer, submit it, or you want us to write it out?
On what? What do you mean?
The coding part of the exam. You want us to
it's gonna be on the computer. So when you write the exam, you will write one part would be on well, everything will be on the computer actually. So you write your exam on the computer, you submit it on Moodle, and then The coding part, you will code separate, and then you will submit that onto Moodle again. Everything will be onto Moodle. And just like how you've been doing with your projects when you send it in, you'll send in the coding straight to Moodle. Basically the same thing. Yeah. Okay, let's continue, because I think we have a good bit of time that we need to finish this. Okay, let's look at the second part of this. I think we were here. Okay, so in this case, it's you have another program, and you turn on and off LEDs by the number of interrupts, right? And using assembly language again. And this one is designed for the 2553. And this is another device that has, it's not the thumb, but it's a, I think this one has, I think this is from another device from another guy's doing something else. So it's not the same device that I was using for class, but it's another device that's kind of like in the 2 family. So it's kind of limited too. Okay, so the code has been altered to fit the 5529 device, and so that's why there might be some changes. And hopefully the translation is good, and not with. Because I don't know if we tested this thing, but let's see what the translation is, and it has to make sense too. So, okay, so the first thing from this, it says, so you move from P1 the directions, you change the or you assign the P1 direction as output for P1.0. That's output, and also the P4.7 as output as well, and also on P1 out, you want to reset that correctly. Okay. Anyway, so that's reset, and then you move. No. You're writing a 1 to the P1 out. Sorry, that's yeah. Write a 1 to P1 out, so that means you're turning on the pin at P1 out point 1.0. You turn that pin on. You're also turning on the 4.7. That's that. This one gives you direction as output. This one is actually writing to the pin, right? Okay. The next thing you do is you're writing to pin 2, and again this will be P2. I don't know why I'm messing that up. Okay, so that's P2 out as well. And this is the P2 enable, and also this is enabling the what's that called again? The pull-up resistors. So you're enabling the pull-up resistor, and this is actually writing to the pull-up resistor to actually to activate it. Okay, so once you enable it, you're actually writing.
Question: why are you thinking P2? I mean, pin 2 again?
Huh? Why are you doing what now?
Why do you think it's P2 again?
Okay, so it's P2 because you're on pin. You're on the port on the device. It has on this.
Oh, it has a P2 in.
P2.1, yes.
Oh, okay, got you.
Yeah, so that should be a P2.1, and that's why I said it's a mistake. Yeah, switch is on P2.1, and the other switch is on P1.1.
Right, so they're writing the P1.1.
Oh, I think you're right. You're right, absolutely. There's 2 switches, one on P1.1 and 2.1. Okay, yeah, I stand corrected by far. So I just changed the pin for the last example. So the pin from the last one was a P 2.1. I changed it to a P1 from a P1.1. So and this one is the P1.1. So actually, there's a switch let me see what the switch number is again. Switch 1, yeah. So switch 1 is P1.1, and switch 2 is 2.1. So okay, yeah, you're right. Mr. Strap is right. I'm wrong. Okay.
Give me some extra point somewhere for that now.
Yeah. So point of correction on this one. So yeah. So he's right. So there's some logic to this. Okay. So this is P1.1, and this one pin again. This is 1, so that's 10. So that'll be P1.1. The same for this one, P1.1. So pull-up resistor is activated, and then you also have this on P1.1 again. The enable, right? The interrupt enable, and of course you have on the edge select. This is on the high to low edge, and it's going. Is looking for whenever the transition is from high to low, and then it looks at the next one is the flag. So the flag is reset or cleared. For some reason, there's a R5 that's cleared. So R5 is cleared as 0. Something might be going on with R5. Maybe that's a count. Okay, and then bit set. We enable interrupt so setting the bit for the IS for the GIE on the status register. Okay, so this is enabling, or this masks your interrupt, and so it enables the interrupts for all interrupts that are there. It enables them. Okay, and then it's going to jump to this $sign. So jump pretty much to NOP. Okay, so it just waits there until there's an interrupt. That's all this program does. Wait until the interrupt. There's nothing else to worry about in this case. So now we have the interrupt service routine. So what it does is increment R5. So from R5 is 0, we look at it now it's going to increment it by 1. Then it compares to when it gets to 4. So as the interrupt as it increments, it's going to look to see when this number gets from 0 to 4. So you want to do this 4 times. Then jump if equal to red LED, and red LED has this bit of so bit set P1.0. You're gonna apply a 1.1.1, turn it on, and then turn off 4.7. Okay, then you clear the flag for P1.1. This is the switch, right? So that's cleared. Then you return I, so return from the interrupt. Okay. Then so this is the red LED. This is on the right side of the board, I guess. Okay, and then then it's gonna go back to return I means it's gonna go back up here. Red LED is going to go back here and compare to see when it reaches number 6. Okay, and then once it compares with number 6, and then it's going to go to the green LED if that is the case. If not, it's going to go on. Okay, and it's going to clear the flag number 2, and then it returns from here. This interrupt, it goes away up there. So in either case, you still want to make sure you return on each of these also. So for the green LED, you turn off P1.0 and you turn on P4.7. This is the other LED.
So what day was it to be turn on, turn off? Or you just said that?
So when you turn one on, you turn the other off, basically. You don't want them to be on the same time. So if you turn one on, you're going to turn the other one off, basically.
That's all.
Yeah.
I saying what how you know it to turn off? How you said that just now?
How do you know it turned off?
That's all.
Oh, because of the bit set. You're setting your bit. You're setting this one to 1. If it's clear, BIC, that means clearing that's that very bit. It's not an XOR. Maybe we're using the XOR function. In this case, you're just setting the bit directly on this pin.
Well, BISB means off and BIC means on. That's what John said.
Right. Now, yeah. Okay, so now let's take a look at where was I on this one? So green LED and did I go past something? Okay, let's look at this again. Okay, yeah, all right. So I'm back to the green LED and red LED. So once we're done with this, it clears R5. So notice that it clears R5 to 0 again. And then also it clears the flag for this one as well. P1.1, and then return I. Okay, that's it. Okay, and then make sure your ports are in. So you have your reset vector and your system reset. Then you make sure that your port 1 and the ISR are included in that definition, and then you're done. So this would be a good program to run and see if it actually works. I think it does work though. Okay, then yeah, I think that's supposed to be functional. And the next thing is, what do I do next on this? I think there's some applications that it also looks to. Okay. All right. So in this case, let's look at what these applications would be. So in the real world, you consider many different things to use with something like this, and some examples that includes, say for example, if you have equipment list, we have capacitors, regulators, stepping motors, or stepper motor, motor drivers, push buttons, LEDs, resistors, and 5 volts DC adapter. Now, if you know what your stepper motor requires, right? For example, a digital pattern or rotation sequence to be fed, so that the rotation is activated, then you can have a washing machine that can be controlled by 5 push buttons. Right? So 2 of them are the main on-off switch and rotation speed. Then the remaining 3 buttons are for selections such as pre-wash, normal wash, final wash. And when the system is activated, the main LED is turned on. In this state, all wash cycles and all programs can be performed. Each program is specified by a specific button. There's also an extra button to control the motion or the speed, rotation, to slow or fast. Then when the main button is pressed again, the system will be deactivated. So this is to indicate this, the red LED is turned off. All of the functions of the washing machine will be supplied to and controlled by the MSP430. So you can actually look at this device as a controller for processing a washing machine if you so desire to try. I think this is a nice project to implement, actually. Okay, so then there's some other things I think was written in this document. Of this document, I think. So you can read this rest of this. Okay. Okay, I think this is the end of interrupts. There are many things we can look at for this course. Of course, this is the last week. There are many things, and one of the more interesting things that you can actually apply or get some results from if you are working on, say, motors or something like that, are your timers. If you have, say, for example, a motor control project, then you would want to work with, say, your timer A or timer B. and use your capture and compare functions to give you, for example, pulse width modulation. And those, when you do those things, you can either capture or you can compare. When you send a pulse width modulation signal out, so that means you are actually, you're not capturing, you're now comparing, right? And when you send a pulse width means that you can kind of vary the pulse of something to either speed up the motor or slow it down. The more it's on, the more fast it will be. The more it's off, means that you're going to average the. Let me see if I can draw this properly. So if you have, say, a motor, and you have a transition, and you're very much off for a long time, on again. I'm not drawing this straight. Let me just cut it down. Short. I'm not getting that good at it. Okay, so let's assume that's your motor, that's your PW, pulse width modulation. So the width of the pulse is what we're looking at. So then your average would probably be something like, this is your voltage, basically. Sorry, not that low. So this is your voltage. Sorry, let me see if I can draw this better. Hope you can see this, what I'm trying to do. So basically, your average voltage is like that. Now, if this thing is on more, let me see if I can start. Anyway, so if it's on more than off. So this is more on than off. Then your voltage is going to be up higher, so it's going to be up here. So this averaging, right? It's not going to be completely on, but it's going to be up high. So I'm kind of dropping in the voltage. I'm not drawing this very well. So that means your voltage, your DC voltage is going to be up higher, the average, right? Of course, you're going to have a capacitor that filters out these transitions, and so on with this too. You can have a capacitor. Actually, the motor is an inductor itself. The big old fat motor will make this look like a filter, right? So then in that case, then your inductor be fat enough to absorb all of this energy and this transition, and the voltage will look like a low level. If it's more on, then the voltage here would be a higher voltage, and so that's why your motor would speed up. So if you're able to control this PWM, and your processor can control these things, then you're able to be very decisive in your motor control, right? And that's how you work this out. And so those timers are important, because what timer does is you have switching, and this is like the sawtooth waveform that goes. Sorry, I messed that up. Sawtooth, I messed that up again. Messed that one up too. Crap, why can't I get a straight line? Yeah. Like that. Anyway, so now if I average this out, like right there, I can pull out my waveforms right here. Come down here. Yeah, there's another one. Right. I'm lining up with this thing there. On, this off. There, off. And so this is my PWM I'm creating, right? As I create this, and to control this, all I do is make sure I can take this line and drive it up. So if I drive this up, this is now gonna shoot this off more, right? And so now I'm limiting my. This is the right in this area. I'm limiting my output on my PWM. This is what I'm limiting it to. instead. So as I say, move this up here instead, that's what I'm doing, right? If you see what I'm trying to point to, all you have to do is vary this line up here. So then as I compare or come down here, this is going to be more on, right? And as I shift this up and down, I can get my PWM to change. So this is what you call PWM control. And so this is my capture and compare on my timers. You can actually implement something like that. Okay, so anyway, that's the idea, and you'll see that in your textbook. Will show you something on when you deal with your timers A and B. You can also look at your user's guide. That's what you want to get to. So nifty things like this would be sweet to work on with this device and your timer. So that's something you can look into later date. The next thing you might want to look at is your analog to digital conversion. So that means taking, say, for example, a temperature. Let's assume that your temperature rises linearly. So you have a temperature sensor within this range to this range. So you can actually read in points. So when the temperature is, say, 78 degrees here, something like that, or let me say 80 degrees there or something, you can actually read in these data points. And let's assume that you're calibrating your voltage from this is your max, say this is 100 degrees, so say this is 0 degrees here, say, let's assume 0 degrees. So between here and here, the voltage will be like 3.3 volts, and this will be 0 volts. You can actually calibrate this on your sensor. Your sensor is going to give you these voltages. You can translate this voltages now to degrees, and you can actually read in your temperature. So once you read in your ADC, this is your ADC. Right. So when you read in that into your memory, the ADC memory, you can actually get these points, and according to your temperature, you can actually say change your window to more open or less open. Let's assume you have a motor on the window. You can actually change it depending on temperature and regulate the temperature in some environment. That's another way you can look at it too. That's how your device could be used very effectively. Okay, you can do it on and off too. So if let's say you have a set of windows that you want to turn off on and off, then you would do that.
I mean, it's not. It sounds just like how when we use the truth table basically on a line or graph, I'd say.
A what now? Say again.
I mean, like we do drawing, it sounds like we're doing on the truth. How we deal with the truth table? Can you say like put it on a line or so, on and off that state?
If you say a truth table, you're turning what on exactly?
I mean, like the output, I'd say, yeah.
Okay, I guess if you have several windows that you might want to turn, well, I guess if you turn it on and off for a while, yes, you can do that that way. Yeah, the on and off would be like, for example, if you have a water heater, you turn it on for a while and then off again. Your heater just heats it up for a while and then turn it off again. Yes, that's a on off control. That's a simple control.
Awesome.
Yeah. Okay, that's it for today. I don't think I want to go further onto this, but those are some other things we haven't really looked into. So those are things you can look up on your own. Then there's some digital communications things that they provided also on this and this device. You can transmit and receive data, so you can look at wireless and those kind of things. All right, let me call it quits for today. So that just gives you an idea of what the capability of your device. We haven't even touched the surface of that yet. Too bad we couldn't get to those. This class really needs another session. like microprocessors 1 and microprocessors 2. Do things like that. Alrighty, take care. I'll see you on Thursday. I think that's the last class, and we'll try to get a review in at that point. And any questions you have, you can just you can look at that. Okay, see you later. Take care. Let me take the medicine before you go. Let me do that. Sorry. Don't leave yet. 1, 2, 3, 4, 5, 6. Did anyone drop before I said 1, 2, 3, 4, 5, 6? Who's not here?
Justin, I think.
Was Mr.
One person left like 1:30. I don't know if Borrow.
1:30. Oh, Bowes left, eh? Okay.
He left 1:30.
Yeah. Okay. So everybody was here. All right. I'll fix the register so that it reflects that. All right. Take care, people. Thank you very much.
Later.
All right. Let's find this register. 19.